Good day to all of you. In this video, we will study the um, publication paper published in IEEE European Test Symposium ETS in 2019. This is kind of audiobook and video book of this published paper. The presentation topic is, or paper name is, Feature Engineering for Recycled FPGA Detection based on WID Variation Modeling, published by Foisal Ahmed, Michihiro Shintani, and Michiko Inoue from Nara Institute of Science and Technology, Japan. Abstract of this paper is: we propose a novel recycled field programmable gate array FPGA detection method based on within-die or WID variation modeling. Model parameters extracted by the WID modeling simply but accurately represent the process variation of each FPGA, and thus, by using the model parameters as feature vector, machine learning effectively classifies target FPGAs into fresh or aged. Through experiment on commercial circuit simulator, the proposed method achieves 99.6% feature vector size reduction per FPGA, with showing 96.0% detection accuracy. While our silicon result using commercial FPGA demonstrates the model parameters have a good distance properties between fresh and aged. Introduction. Recycling of field programmable gate array (FPGA) is now an emerging concern due to reliability and security. In order to detect the recycled FPGAs, several methods positively using the increase in path delay induced by aging have been proposed. In one or proposal 1, the basic idea of the recycled FPGA detection using ring oscillator or RO frequencies is provided. In proposal 2, the ROs are designed one by one in all logic blocks. The inherent spatial process variation of the measured frequencies is extracted from the ROs as a unique fingerprint or FP. Using one-class support vector machine SVM, the RO frequency degradation between recycled and fresh FPGAs is recognized. However, as increasing the number of the measured ROs, the detection accuracy will degrade due to curse of dimensionality, because the frequencies are used as they are as feature vector in the existing methods. In this paper, we propose a novel recycled FPGA detection method based on within-die or WID modeling. Through the WID modeling, systematic and random components of the frequencies are extracted and effectively used as the feature vectors in the machine learning or ML-based classification. 2. WID modeling or WID modeling based recycled FPGA detection. The overall flow of the proposed method is illustrated in Figure 1. Our method assumes the existence of golden or known fresh FPGAs. First, the ROs are designed on all the golden FPGAs and the FPs are measured. Then extracts the WID model parameters from the FPs. The parameters are fed to the ML as training data to train a classification model. Before an FPGA under test or FUT, is implemented into system, the FP of the FUT is measured and modeled by the WID modeling, WID modeling in the same manner. Then the model parameters are sent to the classification model. Then the model parameters are sent to the classification model to query whether the FUT is fresh or not. If the FUT is previously used, the WID model parameters are changed due to aging. As a result, the recycled FPGAs can be efficiently detected through the ML-based classification. This is the figure of overall flow of the proposed recycled FPGA detection method. Golden FPGAs from FP measurement to WID modeling, and FPGA under test FUT or FP measurement, WID modeling, aged or fresh. With this comes the training data, this comes the test data. With this logical questioning, is it aged or not? The WID process variation in manufactured LSIs is generally divided into random and systematic components. The random component comes from random phenomena such as random dopant fluctuation. The systematic component, in contrast, is often modeled by polynomial equation of coordinate location xy on a die. The measured characteristic function of xy, each frequency in FPGA, is expressed as f of xy is equal to s of xy plus r of xy, where s of xy and r of xy are the systematic and random components, respectively. The higher order polynomial for the systematic component gives a well-fitted model but consequently inclines to overfitting problem. To tackle this issue, the proposed method derives the suitable order on the basis of Akaiki's information criterion AIC as proposed in 5. The random component is extracted by subtracting systematic component from the measured characteristics such as or r of xy equal to f of xy minus s of xy, and is represented as a normal distribution of the zero mean and standard deviation of sigma RND, sigma random. If we find that the third order equation is the best predictable model from the AIC, then the third order polynomial of the systematic component s of xy is written as follows: s of xy equal to a0 plus a1x plus a2y plus a3x square plus a4xy plus a5y square plus a6x cube plus a7x square y plus a8 xy square plus a9 y cube. Equation 1, where a0 to a9 are the coefficients in the recycled FPGA detection. The coefficients and sigma random are utilized as the feature vector in the ML. In this case, the length of the feature vector is 11. Here, we would like to note that the order determined from the golden FPGA's third order in this case is also used in the WID modeling for the FUTs. Experimental results. A. Measurement. An on-chip measurement circuit has been implemented on commercial FPGAs using a 7-stage RO based on an inverter. We placed 3000 ROs in a geometrical grid of 20 into 150 through hardware macro modeling to make a unique FP. We We implemented this same measurement system on 10 FPGAs. Among the 10 FPGAs, only one FPGA called FPGA01 was used as a recycled FPGA. Our measurement was carried by repeating stress and recovery phases with 2 days intervals. For the stress, we used S9234 benchmark circuit, and random workloads were fed to the circuit at 100 MHz. In order to accelerate the aging, the FPGA01 was heated at 135 degrees Celsius using a thermal module. During the stress phase, the circuit was totally powered off. In the recovery phase, the measurement cycle continued for 14 days. Through the calculation of the AIC for the 10 FPGAs, we found that the third-order polynomial model is the best among the various orders. As a fitting result, the average root mean squared errors, or RMSEs of the 10 FPGAs are found less than 0.5 or 0.5 MHz. Figure 2 shows the decomposition of the fresh and aged FPGAs of the FPGA01 into the systematic and random variations. The random components of the fresh and aged FPs almost follow a normal distribution. Through the WID modeling, the 11 parameters A0 to A9 and sigma random are extracted from the FP, which consists of 3000 frequencies. Hence, the result of the dimensionality reduction is 99.6%, is equal to 3000 minus 11 divided by 3000. It comes from this equation. Here is the picture 2, where this figure shows the systematic fresh, this shows the systematic aged, this shows the random fresh, and this shows the random aged, which shows actually decomposition of the width variations of the FPGA01 from the fresh and 14 days aged. Figure 3 depicts the change of the parameters of the FPGA01 as a function of the aging time. In Figure 3, all lines are shifted to start from 0 value in order to clearly show the temporal change. During the stress phase, the large changes of some parameters can be observed. Among them, A0 and A2 severely go down. In particularly, A2 reaches minus 0.141, which is equivalent to 14.1% of the normalized range. This figure shows the figure 3 of temporal changes of 11 model parameter of the aged FPGA01. Where we are seeing these two are downing and others are not so downed or declined. B. Numerical experiments. We conducted a numerical experiment to create B. Numerical experiments. We conducted a numerical experiment to create 100 fresh and 14 aged FPGAs using a 7-stage inverter-based RO on commercial circuit simulator. We mimicked the systematic and random components of threshold voltage deviations of NMOS and PMOS transistors as reported in 6 and 4, respectively. In this numerical experiment, we fixed the temperature at 27 degrees Celsius and changed the year of aging as 1 day, 1 week, 1 month, and 6 months. For negative bias temperature instability induced threshold voltage degradation according to 7. One class SVM is used as the ML algorithm, as we used a third order in the WID modeling to represent the systematic component. The size of the feature vector is reduced to 11 from 3000, 99.6% reduction. Figure 4 shows the receiver operating characteristics ROC or ROC, where we can be observed that as the time of usage increases from 1 day to 6 months, the ROC curve moves to the upper left corner. Also, the area under the curve increases as the aging time increases. This is the figure 4, which shows ROC curve of our recycled FPGA detection, and we are seeing the different values and figures here. Conclusion. We proposed a recycled FPGA detection method by exploiting the suitable feature vectors based on the WID modeling for the fresh or aged FPGA classification. Experimental result using a commercial FPGA shows the effectiveness of the model parameters in the recycled FPGA detection. Numerical experiment using a circuit simulator also demonstrates that 96.0% detection accuracy over for 1 week aged FPGA, with achieving 99.6% feature vector size reduction for each FPGA. Acknowledgements. This work was supported by Telecommunications Advancement Foundation. The part of this work is also supported by a JSPS Kakanhi grant number 18K18025. These are the references. The first one is of H. Dogan et al. Paper name is Aging Analysis for Recycled FPGA Detection in PROC DFT 2014. Second, V. Jyoti et al. Paper name Fingerprinting Failed Programmable Gate Arrays in PROC ICCD 2017. Third, B. Sholkopov et al. Support vector method for novelty detection in PROC of NIPS 1999. 4. S. Saxena et al. Variation in transistor performance and leakage in nanometer scale technologies, IEEE transaction on Electron Devices Volume 55, 2008. 5. T. Sato et al. Determination of optimal polynomial regression function to decompose on-die systematic and random variations in PROC ASP DAC 2008. 6. T. Takahashi et al. On die parameter extraction from path delay measurements in proc of ASSCC 2009. And 7. S. Bien et al. Nonlinear delay table approach for full chip NDTI degradation prediction. Thank you very much to all of you to listening and viewing this audiobook and video book of the paper named Feature Engineering for Recycled FPGA Detection based on WID Variation Modeling. I am Tanvir Ahmed Tariq from Dhaka, Bangladesh. Thank you so much. Good day to all of you.